All right, ladies and gentlemen, this I'm sure is the moment that you've all been waiting for. So we are going to find derivatives now from the definition of the derivative. So prior to this moment, we've only been able to find derivatives on our calculator or estimate them using our average rate of change. By the end of this lesson, you're going to be able to find a formula for the slope of a curve. So this is really an exciting moment in our math careers. The way we're going to approach this is through our average rate of change formula that we've been working with. So this is a way we've estimated the slope of curves before. And we're going to use a problem we've actually done before. We saw this in the very first unit. We have the position of a car, and we're finding average rate of change of the position. We all know now that this is a velocity problem. And I gave you the first couple velocities, right? So that's the table filled out. And notice that as my interval gets smaller, my velocities go from 2.1 to 2.01 and so on. Our velocity is going to be 2. We can kind of see that trend, but we don't know how to prove it yet. So the way we're going to tackle this is we're going to look at this interval from 1 to h. So I've filled this out for you now. We're plugging in h. And the reason we need to use this h, right, is if I try to use 1 to 1 to find the velocity at t equals 1, I get this 0 over 0. And 0 over 0, as we know, is undefined, so that we get kind of stuck there. So the problem that we're trying to solve is if I know this point is t equals 1, and I want to know the slope at that particular point. In other words, what would the speedometer of the car say at that particular point? I cannot use this interval 1, 1 to calculate that value, right? By the way, this is called a tangent line, and what it represents is the slope of the curve. Right, so the slope of this line, whatever it is also the slope of the curve. So notice it touches just at that point, and it is kind of parallel to the curve. Okay, so the way we're going to do this is we're going to use an expression, right? So this expression for average rate of change is equivalent to this. And the way I got that is using my function s of t. So h squared is h squared, 1 squared is 1. Right, so I'm just plugging in values to this formula. And now, if I have that function, well, this is my average rate of change. This is going to be cool. You're going to get goosebumps. I want to make this very small. I want to know what happens as h gets closer and closer and closer to 1. And this is now a problem that we can solve from last year. So this is why we spent all that time studying limits. So I can factor, this is a difference of squares, and then my common factors cancel out, and now I can plug in 1, and I get 2, and that's my derivative, that's my velocity, 2 meters per second. Let's add our units, 2 meters per second. That's it, we found our first derivative. Notice it's exactly what we'd expect from the table. And notice, we just combined two math problems that we already know how to do. So I want to take the average rate of change over an interval that is infinitely small. So, well, I write a formula for it, and then I take the limit as that interval gets smaller. And this literally changed the world when it was invented. So this method allows us to solve problems we could never have solved before without it. Okay, now what I promised is to find a formula for the derivative, right? So a formula that will tell us the slope of the curve at any x. And to do this, we're going to use a specific definition of the derivative. So I'm going to use the interval from any x to x plus h is my interval. And h is going to represent the change in x. Sometimes we use delta x, right, to represent that. That means the same thing as h in this case. And then I'm going to do average rate of change. I'm going to use colors for this. It'd be helpful, I think, in your notes if you also use 2 different colors, because we're going to use this problem, or use this definition on the back. So what I'm writing is just my average rate of change formula. my slope formula. And then I'm going to take the limit of that as h goes to 0. So I'm making my formula, my limit, my difference in x very, very small. So this is the limit definition of a derivative. And notice on the bottom, I can actually simplify that right away. Those x's cancel out. So I'm going to rewrite it one more time. And again, I'm going to use 2 different colors to make our lives easier in the future. Just h is left on the bottom, and we're taking the limit as h goes to 0. And this is going to be the definition of the derivative that you use on your delta math. So highlight it, draw a big box around it, whatever you need to do. This is the definition that we need. So now we're going to use this formula on this next page. So notice we're asked to find the equation of the tangent line. So imagine what this would look like. We'd have a parabola, right, is f of x, and then we have some line that just touches the parabola at a certain point, x equals 9. Right, so that's what we're trying to find, and that tangent line is important because it represents the slope of the curve at that point. So notice I need 2 things to use this definition to find the derivative. I need f of x plus h, and I need f of x. So we'll do f of x plus h first. What that means is I just plug in x plus h for x, and I can expand this. And you can use a Punnett square to do this. You'll probably have this memorized pretty quick. And then f of x, well, that's just f of x. Right? And now I can use my definition. And I'm going to call this now f prime of x. So this notation represents the derivative of x, and that's what we're finding now. That's going to be the limit from my definition as h approaches 0 of, and notice I'm using my colors again, f of x plus h minus, and we're subtracting this whole thing now, so we're using parentheses, minus f of x all over h. And notice I cannot take the limit right away because plugging in 0 gives me a 0 on the denominator, so I have to simplify. So I'm going to start by distributing my negative. Nothing else did I change. And if you've done this correctly, things start to cancel. So notice I have a minus x squared and a plus x squared, and I have a minus 7 and a plus 7. So what I'm left with is this, right? And notice we have a common factor of h. So if you've done this correctly, you are going to be able to factor and then cancel out the h on these. So I undistributed an h, right? And those cancel out, and then I'm left with the limit as h approaches 0 of 2x plus h, which when I plug in that 0 just ends up being 2x. So that is f prime of x. That is a formula for the slope of my curve. Okay? Now, let's say I want now my slope at x equals 9. Well, slope would be equal to f prime of 9, which would be equal to, in this case, 18. Right? So that is my derivative at x equals 9. We need also that point, right? So to write the equation of a line, you need a slope and a point. Well, obviously that point's going to be 9 comma something. We need a y value. That y value is not going to be f prime of 9, but going to be just f of 9. So what that means is I plug in 9 to my original function, which is x squared minus 7. So it would be 9 comma 9 squared minus 7, which would be 9 comma 74. Right? So those are the 2 things we need. From there, we're going to find a y equals mx plus b for our tangent line. I'm not going to show you that here because you guys are already very, very good at that.